All right, hope everyone's doing well. We're going to start the chapter on alkyl halides. Well, we started that in lecture 26, and just a couple comments. So this is definitely the hardest chapter that we're going to cover this semester. There's the most new material. It's very dense, and what's particularly challenging about the content of this chapter is that there aren't a lot of hard and fast rules that, if you learn this correctly, you'll come out of this chapter not with so many rules and sort of things that are well defined, but sort of contributing factors that you have to balance against one another. And so guidelines, if you will, so things that could be better or worse, but often the binary sort of all or nothing cases are rarer. And so anyway, so we're going to try and titrate in this material very slowly. We're actually a little bit ahead in terms of my lectures, and I'm not sure, it seems we have more lecture meetings than we usually do in a live classroom. I know that's probably not true, but at any rate, we're on track to have a couple extra lectures at the end, and so we can take our time here. I'm going to introduce all of the characteristics of SN1, SN2, E1, E2 very slowly, and then at the end try to bring it all together to give you a couple different sort of points that you need to be able to think about: structure of the substrate, structure of the nucleophile, solvent, leaving group. Those are kind of the four things that we need to learn about in this chapter. All right, so we're going to begin with the SN2 reaction. Hopefully, I apologize for the audio in lecture 26. Hopefully you either watched it with my garbled audio or you had time to watch the new version. And so in that lecture, I introduced a little bit of kinetics. We talked about the rate expression for an SN2 reaction. It's dependent upon the concentration of substrate and nucleophile. We talked about what SN2 actually means, substitution nucleophilic bimolecular. And we talked a little bit about the transition state and the orbitals that are involved. But let me just start with a little bit of review in case you haven't seen it. And then also this is going to be very relevant to what we discuss today. So okay, so general SN2 reaction, we've got our nucleophile. This is the group that is coming in and will bond to carbon. This is referred to as our substrate, and X is our leaving group. Okay. Nucleophiles always have a lone pair because that lone pair of electrons is going to be involved in the displacement. They are often negatively charged, though not always. And so you might imagine if something has a negative charge, it's more willing to give up its electrons. And that is absolutely true. And that's why these things are often deprotonated. But again, you can find neutral nucleophiles for sure. All right, so the nucleophile attacks the substrate, and we said that it comes in from the backside, okay? And the leaving group takes the electrons in the CX bond with it. And so I'll first draw the transition state for this reaction. So the SN2 reaction proceeds through a single transition state. okay? Okay, and in that transition state, you've got partial bond formation to the nucleophile. The CX bond is starting to break. It's elongated. It's now only a partial bond. And the carbon, most importantly, that central carbon is trigonal bipyramidal. Okay, pyramidal. And what that means is that the ligands in the transition state, or the transition state, simply put, the transition state is more crowded than the ground state. If you think about the substrate, assuming it's perfect tetrahedron, the bond angles are about 109, right? When you form this trigonal bipyramidal arrangement, the bond angles here are only 90 degrees. So if you just consider the smallest bond angles as your, sort of proxy for compression, we've compressed the angles from 109 to 90, okay? And so you go through that transition state, and then finally you've got your product where the nucleophile has now bonded to carbon and the X group has departed, okay? And the important point is that we have inverted the stereochemistry at carbon. So the 3R substituents that aren't participating sort of get pushed over. They're all coplanar in the transition state, and then they flop over to the other side when the reaction is done, all right? So you can put this on an energy diagram, and it just looks something like this. It goes through a single saddle point. Okay. Let's talk about very quickly about the orbital interactions. So all right, so we're going to use as an example the reaction of fluoride with methyl chloride to give fluoromethane and chloride anion, okay? And so what orbitals are involved? So the F minus is sp3 hybridized, and so it has a lone pair in an sp3 orbital. And to keep it simple, I'm going to leave out the other pairs of electrons on fluoride. Okay, we'll just assume that they're there. They are also in sp3 orbitals. They're all 3 lone pairs are equivalent, or 4 lone pairs. And so there is there's no distinction between them. I just picked one at random here. And then what's involved in the substrate. And so this is where it's important to remember that your leaving groups are almost always going to be more electronegative. The carbon that's leaving will almost always be more electronegative than carbon. I'm trying to think of an example where that isn't the case, and I can't actually think of one off the top of my head. So what that means is that the CX, or C leaving group bond, C carbon chlorine in this case, the bonding orbital is polarized towards the more electronegative atom, in this case chlorine. Therefore, the anti-bonding orbital is polarized towards carbon, and it has a large lobe behind carbon. Okay, so I've drawn sigma star CCl there. Okay, so what I am showing when I draw the mechanism at the top of the page, you know, with the red arrows where I just start pushing electrons. What's actually happening at the orbital level is that you have a lone pair on fluorine in an sp3 orbital attacking the sigma star of the carbon chlorine bond, or the carbon leaving group bond, okay? And when we get to the transition state, then we know from the discussion above what the geometry looks like. The question is, what are the orbitals, okay? And so if you just think about the carbon, don't let the partial bonds to the nucleophile on the leaving group, you know, sort of confuse you. Carbon has 3 complete bonds. It has 3 discrete bonds to hydrogen, okay? And so those adopt a planar arrangement, and you have a 2p orbital that is perpendicular, that is interacting with both your nucleophile and your leaving group. Okay, so what we say is that, and this is partial minus, this is partial minus. In the transition state, the carbon is sp2 hybridized. And C2p interacts with the nucleophile and the leaving group, okay? And so two comments. So one is that you might be getting a little uncomfortable here because it looks like I've got 5 bonds to carbon, 10 electrons around carbon. That's a violation of the octet rule. The response is that these aren't full bonds, these are partial bonds, okay? And so we aren't violating, when we talk about violating the octet rule, we're really talking about ground states. You know, draw me a species with, you know, 5 bonds to carbon, 5 discrete bonds. That's not really what we're showing here. What you actually have, and I'll show you this with some Spartan modeling, is, you know, your nucleophile's coming in and it's just starting to interact with carbon, and your leaving group, because the carbon's picking up this extra electron density into the antibonding orbital, that CX bond is lengthening. It's getting weaker and weaker and weaker. It's no longer a full bond, okay? And so this type of structure, even though, you know, sort of at a superficial level, it looks like there's 10 electrons around carbon, it's still okay because we're not arguing for 5 complete bonds. We're saying 3 full bonds plus these 2 sort of partial bonding interactions. The second thing is the change in hybridization. So I'm going in the ground state from sp3 hybridized at carbon to a transition state where I just said it's sp2 hybridized. And so you may be thinking, you know, wait, you can't change that, you know, how do you just change the hybridization? And important to remember, hybridization is dynamic, and it's simply what the molecule, it's simply the state the molecule is adopting in response to some sort of ligand field. And so as we change the ligands around carbon, it can change in a dynamic fashion to accommodate, you know, in this case, the introduction of a nucleophile. So it's perfectly legal to change the hybridization as we move through the transition state, and then to change it back again as we get to the product, okay? So let me just complete this by drawing the product over here. And so we then have our fluoromethane, and that is bonded to carbon. Our hydrogens have flipped over. This orbital is the new sigma bond, and I have chloride sticking out, okay? So, so the geometry is you get backside attack, okay? The molecular orbital basis for that is that you have this CX antibonding orbital that has a large load behind carbon. Because you get backside attack, you always get what we say is inversion of stereochemistry. So let me just show that here. So going back, we said that all the substituents at the top here were on the left. They get flipped over to the right in the product. And the reason is that I have this backside attack that pushes everything over, okay? And then the key orbital interactions are between sigma star of the carbon leaving group bond and the lone pair of the nucleophile. And in the transition state, you go through a moment where the carbon is sp2 hybridized, okay? All right, so I want to talk, so we're going to introduce the 4 factors that influence an SN2 reaction, and we'll see these for the other reactions in the chapter. So when we talk SN1, E1, E2, it'll be the same 4 factors that we need to think about. So we're going to introduce these factors slowly. We're going to start with the structure of the substrate. Okay, this will take most of today's lecture, and then we'll get into the other 3 factors: the nature of the leaving group, the nature of the nucleophile, and last but not least, solvent effects. Okay. And so these are sort of listed in order of increasing kind of difficulty or increasing level of ambiguity. The structural effects on the SN2 reaction are relatively straightforward, and you know, you kind of have a couple limiting cases that make it easy. As we get to the leaving group, the nucleophile, then the solvent, it becomes more of a sort of, you have to consider those in the context of other factors. And so anyway, so we'll introduce these 4 things. It's going to feel like a lot of material because it is, okay? But as we cover them in the SN2, you know, the same types of trends, the same effects are going to emerge for every other reaction in this chapter. So, you know, if you can understand how these 4 things affect the SN2, you'll probably, hopefully, be able to extrapolate those effects to these other transformations. All right. All right. So we'll start with substrate structure. And so the first thing to keep in mind is that, excuse me, the transition state for the SN2 is more crowded than the ground state. So in the starting materials, carbon is sp3 hybridized with 4 ligands. In the transition state, the carbon is sp2 hybridized with 5 ligands. Okay, and so as I go from that, initial structure, I've got bond angles of approximately 109 degrees. I go up to my transition state, and the bond angles between the hydrogens and the leaving group decrease now to 90 degrees, okay? The bond angles between the hydrogens themselves, between 2 hydrogens, obviously get bigger. They're now 120 degrees, but I have this compression on the side of the leaving group where I'm pushing those hydrogens closer. And they're also then starting to come into proximity of the nucleophile. So what this means is that steric effects. So anytime I make those hydrogens on carbon bigger than hydrogen, the resulting steric effects are going to be felt very strongly in the transition state. Okay, so the transition state for SN2 is very sensitive to size of the groups on reacting on the reacting carbon. Okay, and this is reflected in the relative rates of reaction. So as an example, if one takes acetate and allows this to react with an alkyl iodide, you can alkylate the acetate and liberate I minus, okay? And so the fastest, all else equal, so not changing the nucleophile, solvent, or temperature, all else equal, the fastest reacting R group is going to be CH3. And so this is just a methyl. And that's followed by CH3, CH2I. So this is what we call a primary substrate. The carbon that bears the leaving group is attached to one other carbon. We then have isopropyl. This is secondary, so that carbon is a carbon bearing the leaving group is attached to two different carbons. And then finally tert-butyl. And this is tertiary, okay? And so we can measure the relative rates of these reactions, okay? And so if the iodo-ethane reaction is set to 1, the methyl iodide reacts 30 times faster, okay? And the isopropyl iodide reacts 100 times slower, and tert-butyl iodide does not react, okay? And so we're spanning about 4 orders of magnitude of relative reactivity if we just look at the methyl to the secondary, all right? And the rates decrease as you increase the substituents, the size of the substituents on the reacting carbon, okay? And this is directly a consequence of this steric congestion in the transition state, okay? So you have to start to replace the hydrogens up here with methyl groups. Those are all bigger. Yeah, Caroline, you got a question?
Yeah, I was just kind of curious about the kcals. That's the kcals that are released from the reaction, or
No,
sorry, what is
this,
that referring to?
So okay, so this is K-rel. So K, this is little k being the reaction rate, and then rel being relative. So they aren't absolute numbers, but we're saying if we call the primary substrate 1, the methyl reacts 30 times faster. Does that make sense?
Yeah, okay. So
Yeah.
basically the tertiary iodo carbon substance, like, well, in theory it might react somewhat, like it's just in such a small amount that we consider no reaction to have occurred.
Yeah, exactly.
Okay.
Exactly. We just say no SN2, and that's, you know, that's a good segue into the limiting cases for this reaction. So methyl is great. You can always, you know, sort of always do an SN2 on a methyl substrate. Primary, also very good. No problems with SN2. Okay. I'm going to skip to tertiary. Tertiary, never an SN2. Never, ever, 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 ever. You get the idea. Never SN2. Okay. So those are the limiting cases. That's easy. The one that's not easy is the secondary substrate. Okay. And this is where we get into this idea that I was talking about, that you have to kind of balance the four factors I listed against each other. So the answer, you know, to the question, is a secondary alkyl iodide a good substrate for an SN2 reaction? The answer to that question is, well, it depends. Okay. And that's the tricky part of this chapter, is that, you know, you get to these gray cases where you need to be thinking about multiple factors at once. Okay. But the reason we start with substrate effects is because, you know, 3 out of 4 of these kind of sit at the limit. So methyl primary, always good. Tertiary, always bad. And then there's only one ambiguous one, which is secondary. So this guy, you're going to be so tired of secondary substrates by the end of this chapter, because every time you see one, it's going to be like a lot of stuff to think about. But we'll get through it together. All right. So we can refer to this carbon as the alpha carbon, the carbon that bears the leaving group, as the alpha carbon. Okay. And so another way to capture what we just said is that as you start to bulk up the alpha carbon, you slow down the rate of reaction quite significantly. Okay. The same then is going to be true for the next carbon atom once removed. And so what we call the beta carbon. All right, so effect of beta carbon branching. And again, so now we're going to use ethyl bromide as our example. The carbon that bears the leaving group is the alpha carbon. The next one is the beta, okay? And so for this substrate, the beta carbon has 3 hydrogens. The generic reaction will be with sodium azide. As we see when we get to talk about nucleophiles, azide is a fantastic nucleophile. It's one of the best nucleophiles that we commonly use. That can do the displacement. And let me draw the product. So that gives you azidoethane plus bromide. All right. And we can list relative rates for these reactions. So if we start with the least hindered one, so just iodoethane, set that K-rel equal to 1. If you replace one of the beta hydrogens in the iodoethane with the methyl group, you slow down the reaction. So now we're about 0.4. So about half that original rate. So alpha, beta, alpha, beta. If you replace another hydrogen with the methyl, you slow down the reaction by an order of magnitude. So Okay. And then finally, if we replace all of the hydrogens with methyl, the reaction gets very slow, and okay, you effectively have no reaction, right? So let me just pause and summarize what we've talked about, and then I'll take a minute for questions. So we're talking about the effects of a substrate on the SN2 reaction, okay? And we've kind of bin those effects into two categories. So one is alpha substitution. That's the degree of substitution at the carbon that bears the leaving group. And we've said that as you increase the substitution there, you increase the number of carbons bound to the carbon with the leaving group, you slow down the rate of reaction, okay? And then we looked at the carbon once removed from that, so the beta carbon, okay? And it's the same type of trend. As you bulk up the beta carbon, you slow down the rate of reaction, all right? And so let me just take a second and take any questions thus far, because we're gonna switch to Spartan and look at these a little bit. Yeah, Ghana.
I guess kind of like expanding on this, would we see a similar trend if we go to like the second carbon removed from like the one attached to the leaving group, or like the third, or so on?
Yeah, so the second would be the gamma. So like if I went out here, one carbon, that would be gamma, right? And the answer is yes, but they get very quickly, the effects get much smaller. And you can think about that as you are, as you introduce more steric bulk, you're definitely going to slow down the reaction. But as you remove that sort of additional steric bulk from the reacting carbon center, the effect is less significant. So there is an effect. It's the same trend, but the magnitude is just smaller. And then I think probably by the time you get to the next carbon delta, it's probably negligible. Yeah, that's a good question though.
All right, thank you.
Yeah. All right, so let me show you some models, and then we'll come back and we'll draw some of this out so you have it. But this I think is pretty cool. So let's see here. Yeah, also I'm going to lose my whiteboards probably, but all right, everyone can see Spartan?
Yep.
Great. All right, so same thing is blocking me. All right, so this is pretty cool. So this is basically bromide coming in and attacking methyl chloride. So the green atom here is a chlorine atom. That's going to be our leaving group. And sorry, this is ethyl. This is not the one I want. Let me just hold on for 1 second. Sorry, yeah, this is the one I wanted. Okay, so this is bromide coming in and attacking methyl chloride. Okay, so Here's our chlorine. That's our leaving group. Here's the methyl carbon. So all together, that's our substrate. All right. And here's our bromide nucleophile. Okay. So it looks like there's a bond to bromine, but this is actually just sort of the software kind of keeping track of everything. This, if we measure this length, it's about 3.8 angstroms, and so that's much longer than a carbon bromine bond. So it's drawn in there, but it's not actually a bond. So you can think about this as basically the starting materials: Br minus methyl chloride. If I measure the bond angle here, we're about 108.2 degrees. Okay, so it's basically tetrahedral, and this is your bromide attacking. All right. Let me add the, yeah, this is pretty cool. So bromide's going to come in. The chart, the red series here is the energy of the system, and it's going to run from right to left as the bromide approaches. And so you can watch this thing coming in, and it's getting closer and closer. And when we hit this structure, we're just about at the peak. It's not quite at the transition state, but it's close enough. Okay. And so the thing to notice here is that that carbon is just about trigonal bipyramidal. Okay. The hydrogens are a little bit out of plane. Still canted a little bit to the left, but not by much, right? And so I've got 5 ligands around that carbon, all right? And this is where the modeling is good, because you can see, we draw these line structures. They tell us nothing about the steric interactions. If we switch to the space fill, so what you're looking at are the van der Waals radii of the atoms, okay? And so anytime you see a flat surface, like between the carbon and the chlorine, that's the van der Waals radii are overlapping, okay? And if I've got a bonding interaction there, that's okay. If there's not an actual bond, that's destabilizing, all right? And so the reason I show you this is to see that, hopefully you can see it, that transition state is pretty crowded. If I replace any of these hydrogens with other substituents, you can imagine that they're going to start to interact with the bromine and the chlorine, and that's exactly the case, okay? And so that's sort of the peak of the energy diagram, and then we continue moving on. You can see that the carbon-chlorine bond is lengthening. The carbon-bromine bond is getting a little shorter, and this is kind of where the simulation stops. But the hydrogens now are on the other side, okay? And so that's the inversion that we've been talking about. So let me go back to the beginning here. All right, so here comes bromide in solution, found the substrate, attacking carbon, going through the transition state, flopping those hydrogens over. Okay, it's kind of like, dancing left and right, right? So it's pretty cool, yeah? So what happens when we start to branch at the alpha position? You replace these hydrogens with carbon, it gets more hindered. Okay, I didn't actually model that because I think that's, intuitively that should be okay. What I wanted to show you was what happens when you branch at the beta position, okay? And switch to the ball and spoke so you have the same thing. So let me go. Why did I lose that? It's annoying. No, that's not the one. Okay, this is the one I wanted. So this is basically bromide coming in and attacking chloroethane, okay? And you can see that there's a couple interesting things here is that, the geometries look a little weird as it's actually starting to come in. You can see that it's coming across sort of the ethyl group, right? The methyl group over here. But we're approximately linear with respect to the leaving group. So if I measure that bond angle, sorry, I got too many windows here. If I measure that bond angle, you're about 174 degrees, so almost 180, okay? And we're going to continue along that trajectory. The bromide's coming in, and this is where we start to approach the transition state. And there's the pretty close to the peak of the curve, and you can see that the carbon again it's almost planar. Okay, these things are pushed down a little bit, and that's because of the methyl group, but the geometry is approximately trigonal bipyramidal. Okay, and if we go to our space fill, all right, what do you see? So this carbon is our reacting carbon. Here's our leaving group. And so we're okay with, the overlap of the van der Waal radii for those elements because there's a partial bond. What we're not okay with is like this interface here where the leaving group's hitting the methyl group, or this interface here where the nucleophile is hitting the hydrogen and the carbon, okay? And so those are the non-bonded interactions that I'm talking about. And so this is a good comparison to you can compare this to the one we just did with the methyl, where you're coming in, if you do the space fill, you don't really get a lot of terrible interactions. Maybe there's a little bit right here, but otherwise it's okay, okay? And so we're bulking up around that center, and that's going to slow down the reaction. Yeah, Caroline.
Yeah, quick question. So obviously this is an achiral compound just because there's two hydrogens, but if you were to replace one of them with like a deuterium ion, would that, I just kind of want to understand this in terms of like chirality, if that makes sense. Is the inversion, would that cause like an R to go to an S and an S to go to an R and like vice versa, if that makes sense?
Yeah,
or no?
Yeah, usually.
Okay.
So as long as you don't have any funny situations where the nucleophile comes in and then the priorities, the prioritization gets reorganized, So I guess basically as long as the nucleophile has the same priority in those four, relative priority as the leaving group.
Okay.
Then you get an inversion. Okay.
Okay.
But strictly speaking, you can have instances where that would not be the case, and then you might actually start with S and then end up with S.
Okay.
But from a physical standpoint, it's inverted.
Okay. And the reason that you would potentially start with S and finish with S would just be because like your priority numbers change. But like if you're using carbons, hydrogens, and halides, like it's going to just be an SR change.
Yeah. Exactly.
Okay.
Exactly. Yeah. As long as you're as long as you don't have like silicon or something weird, sort of attached to carbon that could, cause problems in terms of the numbering. It'll be an inversion, R to SS to R. Yeah. All right. So that's the ethyl one. And then we can start to build it up. So this is, that's the T-butyl. Let me save that one for the end. Right, so here's one where, go to this guy. We just did ethyl, so CH to CH3, okay? This is now an example of the beta branching. And so what I'm doing is replacing one of those hydrogens with a methyl group, this one in the back here, okay? And what you're looking at is the transition state, the highest point on the curve, okay? And if we go to the space fill, what you can see is that now things are starting to get more crowded, right? So here's the carbon that bears the leaving group. Here's the one that's directly attached to it, okay? And then the beta branch is the methyl group, and that's in the back, okay? And you can see that you don't really have overlap of the van der Waal radii, right? But what is it doing? It's kind of shielding the molecule, right? So my bromide can't come in close to that methyl group. It wants to come in away from it. And so there are less opportunities. There are fewer collisions are going to satisfy the new kind of constraints. You know, it's like, you know, if you're trying to exit a room and you have to get around someone, right? If you, you know, exit randomly, you're going to bump into that person, right? But every so often you might exit sort of around them. It's the same idea here. We're just sort of reducing the number of possibilities that the molecule can engage in, and so then you're diminishing the rate. Okay, and so this is the example if you come in with 2 methyl groups at the beta position. Okay, and again, let me show you the space fill. You can see that it's getting more and more crowded. Now we definitely have some overlap of the van der Waal radii between the methyl groups and the leaving group. The nucleophile still looks pretty good, but this is going to cost us some energy. Okay. And the big one is the neopentyl. Okay. And so this is 3 hydrogens. Sorry, I didn't actually formally introduce that term yet. So this is replacing all 3 hydrogens at the beta position with methyl. When you have that, so this is another way to think about this is I've got a CH2 group with a T-butyl hanging off, okay? And we have a specific name for this, and that is neopentyl, okay? And if you go to the space fill, you can see that things are not good at all. My nucleophile is bumping into one of the methyl groups, and I've got overlap of the leaving group with the other methyl group. So it's very hindered, okay, to get to that arrangement. So I've drawn that arrangement in Spartan, right? But to get there is going to cost me a lot of energy. And so it just doesn't happen, okay? And I just want to end with one thing, which is if you look at your notes, I'm looking at mine. We've got ethyl bromide, N-propyl bromide. The next one with 2 methyl groups is isobutyl, and then the neopentyl. The relative rates go 1, 0.4, 0.03, and
Professor
then
Harson, we're staring at your Spartan. Are you writing anything?
No, I'm not writing.
Oh, sure.
My yellow. Yeah, because I want to come back to Spartan here. Yeah. So the point is that we see a decrease going from ethyl to propyl about 0.5. You know, the next jump is about 10-fold, and then the next jump is about 1,000-fold, right? Not quite that much, 300-fold, right? And so why do we get that sort of steep drop off in rate when we go to the neopentyl? And the answer is found in sort of the conformations of the molecules. So let me just go back to the ball and spoke so you can see this easier. Okay, so this is the ethyl. No, sorry, that is the N-propyl. Where's the ethyl one? There's the ethyl. Okay, and so you can see that this thing is oriented with one of the CH bonds in the adjacent methyl group, sort of pointing towards the nucleophile. Okay, and the reason for that orientation is let me go back to the starting material. If we go back, so this is basically the starting material. Again, this is not really a bond. Okay, just ignore the bromine substituent for a second. If you look at this, what does it look like to you? That's a staggered conformation, right? That's the low energy conformation for the molecule. The thing that kind of hurts from a reaction standpoint is I have this hydrogen pointing at me, okay? And so it can come in, but the nucleophile, I apologize, this is jumping around a little. The nucleophile, as it's coming in, is going to always see that hydrogen, all right? And so if you go up to the propyl derivative, where we've now replaced one of those hydrogens with methyl, okay, again, this is like the starting material. Ignore this bond. It doesn't really mean anything. It's too far away. If we ignore that, we can see again, we've got a staggered orientation in the starting material. And I'm able to put one of the hydrogens close to the nucleophile, okay? If I then replace with 2 methyl groups, so now we're up to the isobutyl substituent. I'm coming in with my bromide, okay? Again, no bond here. If we just look at our carbons, we're fully staggered. That's good. I've still got a hydrogen in there, okay? But then when you get to the T-butyl, you run out of hydrogens. And so this is the starting conformation for that neopentyl substrate, the slowest one. You can see that, ignore the bromine, you can see that the carbon that's reacting is staggered with respect to the carbon that it's attached to. So that's going to be good. But because I got no hydrogens left, I'm stuck with this methyl group facing the nucleophile. And so that's why you get this dramatic drop off in the rate. And basically neopentyl substrates, you know, it's they generally just, they're not good SN2 substrates. So you don't ever see rapid SN2 reactions at those centers. All right. All right, so I'll stop there. That covers most of what I want to say about the substrates. Wednesday, we'll start digging in more on the other factors. I'm going to close up shop here, and I'll say I'll come back at 10:25 to do office hours. All right, thanks.